Greetings everyone. Myself Sirigiri Shravani. So today we are going to present about a project metamaterial based highly isolated MIMO antenna for wireless applications. My teammates are Supriya MG, Srinidhi Gudi, Sushant Gupta, and the guidance of Anita ma'am. And moving on to the introduction part. So currently, MIMO antenna has pulled a lot of attention due to its potential to enhance the capacity and reliability. So for many wireless communication systems, MIMO antenna is playing a key role. So despite of its advantages, there is a one disadvantage known as mutual coupling. This coupling is typically undesirable since it affects the performance of the MIMO antenna and antenna array system. So, what is this mutual coupling? The interaction between the array elements in the MIMO elements degrade the system performance. So, and it also increases the envelope correlation coefficient and increases the channel capacity loss and decreases the diversity gain, and also radiation part is distorted. So these problems may arise when antennas are placed nearby. So to avoid that, we are introducing a metamaterial which is going to absorb the radiation between the two antenna elements. So the main agenda of this project is to reduce the mutual coupling between the MIMO antenna elements. So the proposed antenna is well suited for the many wireless applications due to its low ECC, high diversity gain, high peak gain, low channel capacity loss, and most of all, the very high.
But the blue color part which we are seeing here, it is a FR4 substrate. Here we are using FR4 substrate, just it has a loss tangent and the relative permittivity will be around 0.02 and 4.4, and the two patch antennas will be 3 millimeter wider microstrip lines, and these are the two patch antennas with the LP. With the LP will be the length of the patch and the WP will be the width of the patch, and we are introducing one MIMO strip or microstrip between the two patch antennas of the width 15 millimeter and the length 13 millimeter. Because we are introducing this because to avoid the mutual coupling between the two patch antennas, if
Have mentioned in the introduction and the working methodology, to reduce the mutual induction, we kept one metamaterial in between two antenna, which avoid the mutual coupling, which means that the relations, the dependency of the two antenna will get reduced. If it will affect one antenna, it will not going to affect another antenna. Now come to the to define this whole antenna, we have something called scattering parameter. S11 is not known as input reflection coefficient, which at the 5.8 gigahertz, which is the resonating frequency, you can see we are getting minus 47.6296 dB, which is the more ideal cases. So in the same parallel, we have designed a transmission parameter also, S21, S122, S22, and to design to get the relationship between the dependency, we have something called envelope correlation coefficient, ECC. At 5.8 gigahertz, go to the ECC, we are getting a 0.06 at 5.8 gigahertz frequency that we can observe it here, which shows that dependency of the antenna is very less. And directivity gain, which is the important parameter to govern any antenna, go to the DIB, which is almost equal to 10 at 5.8 gigahertz frequency, which shows that it is more suitable for the wireless application at 5.8 gigahertz frequency. Uh, thank you for thank you, sir, and thank you, everyone. That's all. Done.